Now consider the sun transit outage, and this is another peculiar phenomena that is very difficult to understand by a common person, but as engineer you must understand it. Consider this situation. This is the earth station, this is the position of the satellite, and this is the position of the sun. That means if we draw a line between earth station and the sun, satellite is now situated in between sun and the earth station, right? So during the equinox period, not only does the satellite pass through the earth's shadow on the dark side of the earth, but the orbit of the satellite will also pass directly in front of the sun on the uh, sunlit side of the earth. So what is the problem? If it happens, what will happen? So you must understand this thing. Sun is a hot microwave source with an equivalent temperature of about 600 degree to 10,000 sorry 6,000 to 10,000 Kelvin, depending on the time within the 11-year sunspots cycle at the frequencies used by communication satellite. Mostly it is within 4 to 50 gigahertz. This effect is termed sun transit outage, and it lasts for short periods each day for about 6 days around the equinoxes. The occurrence and duration of the sun transit outage depends on the latitude of the earth station, a maximum outage time of 10 minutes being typical. So actually uh, during that period of time, short period of time, the satellite, usually satellite, the earth station looks towards the satellite, and now sun is there as a background, and sun used to release huge amount of microwave frequencies with excessive high power, right? And the very sensitive earth station receiver is now in front of the sun, right, receiving huge amount of high power microwave. So there is a chance that during that period of time, if the satellite, if the earth station wants to receive the signal from satellite, huge amount of power will enter inside the receiver, and the receiver may not work properly, rather it may be destroyed because of the excessive high power. That's the problem. So what you have to do, simply you have to switch off this receiver. That is the only thing you can do. So during equinoxes, not only eclipse, another phenomena comes into the picture, that is the sun transit outage. As long as sun is actually inside in the background of the satellite, you have to switch off this receiver. There is no other option. So what you can do, you can use another ground station. See, outage is for this particular receiver position at a particular point. But if we have another ground station far away from this location, then obviously at that particular time, that particular receiver may not be uh, under sun transit outage, right? So you can have more than one ground station. So if one ground station is under sun transit outage condition, the other ground stations will work. So that is the way out. The earth station antenna will therefore receive not only the signal from the satellite but also the noise temperature transmitted by the sun that we have said. The added noise temperature will cause the fade margin of the receiver to exceeded, and an outage will occur. This outage may be precisely predicted for satellite system operators with more than one satellite at their disposal. Traffic can be offloaded to satellites that are just out of or are yet to enter a sun outage. The outage in this situation can therefore be limited as far as an individual user is concerned. However, the outage can be detrimental to operators committed to operations during daylight hours. So I'm just read out this whole thing that I have said or mentioned. We have another phenomena called the Doppler shift. Doppler shift is very common for satellite communication. To a stationary observer, the frequency of a moving radio transmitter varies with the transmitter's velocity relative to the observer. That means the frequency is dependent on the relative velocity between transmitter and receiver. If the true transmitter frequency, that is the frequency that the transmitter would send when at rest, is say ft, the received frequency is fr, and it must be higher than ft when the transmitter is moving towards the receiver and lower than ft when the transmitter is moving away from the receiver. So mathematically we can say fr minus ft by ft equal to delta f. Delta f is this one divided by ft, that is equal to vt by vp. Okay, so delta f equal to vt ft by c, that is equal to vt by lambda, but this vt is a component of the transmitter velocity directed towards the receiver, and vp equal to c, that is the phase velocity of light. It is nearly 3 into 10 to the power 8 meter per second in free space. Lambda is the wavelength. So if the transmitter is moving away from the receiver, then vt is negative. This change in frequency is called the Doppler shift. That means that delta f that we have determined is called the Doppler shift, or the Doppler effect, or more commonly just Doppler, after the German physicist who first studied the phenomena in sound waves. But this particular phenomena uh, is not pronounced in geostationary satellite, but it is very severe for LEO satellites or lower Earth orbit satellites, and for that they require to have frequency tracking receivers. So conventional receiver will not work because the frequency will shift, right? Depending on the velocity, frequency will vary. So frequency tracking receivers are needed. So let us have an example. A low Earth orbit satellite is in circular polar orbit with an altitude of 1000 km. A transmitter on satellite has a frequency of 2.65 GHz. Find the velocity of the satellite in orbit, the component of velocity towards an observer at an Earth station as the satellite appears over the horizon, for an observer who is in the plane of the satellite orbit. Third question, hence find the Doppler shift of the received signal at the Earth station. Use a mean Earth radius of 6378 km. The satellite also carries a Ka band transmitter at 20 GHz. Find the Doppler shift for this signal when it is received by the same observer. So period of the satellite can easily be calculated, that is using this relationship. Putting those values, we can get t equal to 6306.94 second. The circumference of the orbit is 2 pi a, that we can easily calculate. So corresponding velocity, since we have already determined the time period, velocity can easily be determined by 2 pi a divided by time period. So it turns out to be 7.35 km per second. So this is the velocity. The component of velocity toward an observer in the plane of the orbit as the satellite appears over the horizon is given by Vr equal to Vs cos theta. So Vs is this one, Vs cos theta is the Vr. Where is the angle between the satellite velocity vector, and the theta is the angle between satellite velocity vector and the direction of the observer at the satellite. So angle can be found from the simple geometry like cos theta equal to RE by RE plus H. So we put the value, it will be 0.86. So component of velocity is 6354 meter per second. The Doppler shift, third question, the Doppler shift of the received signal, that is delta F equal to VTFT by C. So that is equal to Vt by lambda. So here we have the frequency of 2.65 gigahertz, corresponding lambda is this one, 0.1132 meter. So the Doppler shift you can easily calculate. We have already determined this Vt, and lambda is this one. Putting those values, it turns out to be 56.13 kilohertz. Okay, so delta F is 56.13 kilohertz. Now a Ka band transmitter with frequency of 20 gigahertz has a wavelength of 0.015 meter. So corresponding to that, delta F, the Doppler shift for 20 gigahertz, that we can easily calculate, 6354 divided by 0.015, that turns out to be 423.6 kilohertz. So as you can see, for Ka band, Doppler shift for LEO satellite can be very large, right? Requires a fast frequency tracking receiver. For lower frequency that we got is comparatively lesser, just around 50 kilohertz. But for higher frequency, it is much more, like 423 kilohertz. So we need a very fast frequency tracking receiver. So Ka-band LEO satellites are better suited to wideband signals than narrowband voice communications because of this Doppler shift.